All right. So now we've understood how you can digitally sign a message so that you can show that you have the authority, so that you are the legitimate owner of an item or of a piece of information, and that you have legitimately authorized to make an update on the database, right? So you can initiate an update on the database. Now, one of the things though, which is important about blockchains is that the cryptography is not enough. All that you do with the cryptography is that you show that you are the owner of a particular item. So, and this is really something which is often misunderstood. It's like a blockchain is not just about cryptography. It is more than that, right? Because one of the problems arises is Sue here may make a deal with Bob to convert a car and pay her a Bitcoin or anything else in return. But you need to make sure, and then of course you can sign the message and you can send it to the miners, and the miners can put stuff into blocks. But what you really need to make sure is that at the same time, she's not also signing another transaction and spends the same money twice, right? So, and this is quite critical, right? Because, you know, the two, Bob and Sue, so Bob can very well see that Sue is, you know, sends a digital message. And you can see that she has signed everything and that everything is happening, right? So that she is legitimate owner of the money and that she signed a contract for you which goes to him. But, you know, Bob does not know that Sue does not make at the same time another contract with Charles and spends the same money, right? So Bob and or Charles both need to make sure that before a transaction, before they actually give out their part of the transaction, that the money has actually arrived in their account. And I mean, it goes without saying that we also do this in the real world, but we're talking about now an anonymous world where people are possibly sending digital items back and forth across the globe. So what is required is that we understand which of these two transactions that have been put in is actually legitimate. So the order of transactions will matter. And, you know, it's important that there is some form of confirmation that Bob receives of actually having received the money, so that the transaction is, in fact, secure and has occurred. So, this requires also that we understand that we have some consensus on something having happened, right? So this is a basic mechanism underlying it. Now I've got another set of slides where I have discussed this before, but just let me do a retake here, which I do for the DeFi Finance course in more detail. So the basic idea is described often as a Byzantine generals problem. And you will see in a second how that relates actually to blockchains. So the Byzantine generals problem is that you have two generals that want to attack a city and they need to reach consensus about when to attack the city. If one of them attacks only, the attack will be defeated and they basically are unsuccessful. So now they need to make a decision of how to coordinate. The way it works is the general on the right sends a message to the general on the left. Right? And so then says that we will attack at dawn. And then the general on the left sends a confirmation message and says, yes, I agree, I received your message, we will attack at dawn. Now the question is, does the general on the right know that the attack at dawn will happen? Well, no, he doesn't. Why? Well, because he knows that his message has been received, and so that the other guy knows that there should be an attack at dawn. However, the guy on the left-hand side does not know whether or not his confirmation has been achieved. And if the general on the right has not received the confirmation, the general on the right would not actually attack. So the general on the right would send a message back and saying, I have received your confirmation, so we can now attack at dawn. Is that enough? Well, no, not again, because the general on the right knows that the general on the left will only attack if he knows that he will attack too. But then this general on the left does not know that the confirmation message, or rather the general on the right does not know whether his confirmation of the confirmation message has gone through. So he will still not attack. And this goes on and on and on. And the outcome here is actually that they never can achieve common knowledge of both parties being willing to attack at dawn. Now, this is actually not a computer science result, and this is actually a result of the electronic. It's the same result as in the so-called electronic mail game, which is a paper in Econometrica by Arthur Rubinstein. And essentially it shows that achieving common knowledge of something is extremely hard. Now, in decentralized systems, the problem is slightly lower in the following sense is we don't need everybody to agree, right? So in this particular case with two parties, we need two parties to agree. What we need to have in a bigger system is we need to have a situation where many generals can agree, right? So what we need is, and the problem actually is a little more relaxed then, because we just need sufficiently many of the generals to attack. So you need to have a consensus among them. So how does that work? Now let's start with a simple problem, right? So where you have a single general and he tries to coordinate his captains. So what you want is that in the system there's a sufficient agreement on everybody wanting to attack. So, and there's many messages are being sent, and you can see how this sort of alleviates some part of the common knowledge problem. So let's stay with a situation where there is a clear proposer, so a clear starting general who gives the orders, and the recipients are also known. Now it starts with the general sending a message. This is the message which is in blue is T, and he sends the same message to all of his captains. And so what the captains then do is they send a message to all the other captains, right? And so they basically say, let's say in this particular case, they repeat the message, right? So this is again the message T. And so then all of these, what happens is that all of these individuals received the same message essentially, right? So this captain here in the middle received the message T from the general. Forget about that he sent out the messages. He also receives the same message from all the other captains. And so the majority of the decisions that he gets, majority of the messages that he has are all the same. And therefore he will follow what the majority message said. So what we're trying to go for here is that there's a majority opinion comes out in terms of what the clear decision is. And then the rule is that you follow what the majority decision is. All right, now, where am I going with this? Well, let's assume that there is a fault here. So for instance, it could be that there is one of the captains could be compromised. So this could be either he could be rogue, or actually the communication channels that this general have, or this captain have, are compromised. So the messengers get hijacked. So what happens here is that the original general still sends the same message, attack at dawn, and the captains, the genuine captains here, they send the same message that they received from the general and forward that to the other captains. But this captain here, who's compromised in the lower corner, sends a faulty message X to the other captains. So now let's think about what information do all these guys have. Now the ones here in the corner have received message T, and the faulty message X. And the ones here, this one here in the middle has received the same messages. And the one in the corner has received the same message T, and T. Now, what is the majority message that each of these captains have? Well, in each case, the majority message is T, not X. So in other words, they agree that the majority is T, and they will still attack at dawn. So this is important. Now, when we say this captain here is rogue, we still going with the assumption that this rogue captain updates correctly, updates his own, so follows, not updates, but follows the majority decision. Okay, so that's the idea here, is that even though the messages that this person sends out are compromised, because, you know, for whatever reason he could be compromised, he would still follow the majority decision. So we still have a consensus here. Now, imagine, however, that the original general is compromised. So what this general does is he sends 3 different messages. Okay, so X, Y, and Z. And so what these captains do, they send messages to one another, which are X, Y, and Z. And so everybody basically, truthfully in this case, repeats the faulty message. And now what everybody gets is X, Y, and Z. Right? Now actually what they do, they all agree on that there is 3 different messages. And in some sense, this is actually, for reaching consensus, is still possible. It's actually still a good thing. Why? Because they agree that there is no consensus. So as far as their attack on the city goes, is none of them would attack, right? So actually they still have a consensus, which is not to attack. And that is also good. Now the general rule is, and you can show this, is that the Byzantine generals problem requires, in these very simple messaging systems, that no more than 1/3 of the nodes are compromised. So even nodes meaning, anybody who is in the network, including the one that is a sender. So when more than 1/3 of the nodes are compromised, then the system breaks down. Right? And so basically this is the solution of the Byzantine generals problem. So in other words, for a distributed system, in contrast to the one-on-one system where you couldn't reach consensus, in a larger system this is a lesser concern. What you can show is that in the blockchain you can reach a consensus, except if there is no more than 1/3 of the nodes compromised. Now, let's put this back to the problem that we're trying to study in a blockchain. Now, a blockchain like Bitcoin is based on the proof of work protocol. Now, what is the proof of work protocol? The proof of work protocol is many things, right? But you have the miners. The miners are trying to guess a solution to a mathematical problem. This guessing is hard, so they expense computational resources, and then effectively one of the miners is selected at random to be the proposer. In other words, it's not like the proposer has power over it. The idea is that there's a distributed network of miners. None of them has a particular power over the network. We can talk about what that means in a second. So really, of the many miners, one is selected at random. So they cannot predict whether or not there will be the proposer in the future. Now, the cool thing is that the solution to the puzzle that they give is very easy to check. So what that means is that by finding the solution, first of all, they become the proposer for a new block. Secondly, it is very easy to check for everybody whether or not this is legitimate. So there's a consensus that they actually that they are the proposer. And then the digital messages, again, can also be very easily checked of whether or not they're legitimate. So in other words, once you have found a block, you broadcast it to the network. The network as a whole then checks against that, and then sends out confirmation messages. And then if the confirmation messages will give you a consensus of whether or not the update will occur. That's essentially what we do. So the messages, the transactions are sent to the miners. The miners then create a new block of transactions. And the check that they do is as follows. So the successful miner, what they do is they take the digest of the block, they hash it, which is a particular number, and then they try to modify. So they try to modify that hash plus some extra information, which is referred to as the nonce, such that the hash of the whole thing will be a hash that starts with a certain number of leading zeros. Right? This sounds very difficult. I'll show that to you in an example. But the idea is this, again. You take information of the valid transactions, you hash them, that gives you a 64 character output. Then you add a piece of information to it, which is a set of numbers, usually numbers and letters potential, but say numbers, such that the hash plus this number totally hashed together is a particular hash which starts with a number of zeros. That is simply the convention. Whoever finds a hash with a number of leading zeros gets to propose the new block. And you go, okay, so how do you find that hash? Well, you basically just change this nonce, the number, many times over, and you drew the hashes. Right? So, and that effectively is because the change in the numbers is random, so you change them at random. Whether or not you find the hash that actually is effectively a random function. And so the only way how you can do this is by just taking numbers and hashing and hashing and hashing. And this is why we talk about the hashing power of the network, right? Because it depends on the more hashes you can do per second. So that means the more computation you can do per second, the faster it goes and the more secure the network goes. Okay. Now, And this algorithm here is indeed a Byzantine fault tolerant one. Why is that? Well, so the message that the winning miner does, and it sends to all the other recipients, is effectively they send the block, which is the successful block, which is the transactions, and the nonce together, and he sends that out. And then what all of these miners do is they just provide a hash of that information that they receive and check whether it starts with a leading number of zeros. And if they do, they accept it. In fact, they don't actually have to send it to everybody else, they just accept it such as it is. And there you have your consensus. So, what the proof of work protocol therefore does, it does two things. Number one, it selects the leader, so who gets to propose. And it makes also the messages very hard to forge because, you can't just pretend that you are the leader and that you have something legitimate. You actually have to find something which actually has this property of the leading zeros. So there you have it. Now what I will do in the next few minutes is I'm going to go again through the demonstration that Anders has done for us, and I'm going to just narrate that for you. All right, now how does the proof of work protocol address the Byzantine fault tolerance? So here's how this really goes. If you see a message which has, so it uses the zeros as a the hash with the leading zeros as a coordination device. If you see such a message update, you know what you want to do, right? So the mining is difficult and it's very time consuming. So a forger actually needs to work really hard to forge the message and to find something else out. And the message is sent to many entities. So there's a strength in number. So if you are a forger and you're trying to trick somebody, you actually have to try to trick everybody. And so unless there are too many forgers out there that try to send faulty information, then you can trust what is happening. So what the proof of work document therefore gives us is existence of the transaction.